Okay, so let's go through this. So the derivative of this residual sum of squares with respect to beta. So we're going to end up with negative 2x transpose y because this first part drops out, there's no betas in it. The second part only has one beta, and so we end up with just the pieces around it, 2x transpose y. This third part has two betas, and so we end up with 2x transpose x times beta. And so this is what the derivative is. We're going to set it equal to 0 and then solve for beta. So we're going to need another matrix fact for this. This matrix fact is that A times A inverse, so some matrix A times the inverse of that matrix is equal to I, which is known as the identity matrix. And so this is what that identity matrix looks like. It's basically this matrix that on the diagonal has all ones and it has 0 everywhere else. So this is the equivalent of multiplying like a scalar times 1. If you multiply a matrix A times this identity matrix, you always get back the original matrix A. So it's sort of like just multiplying by 1, but in kind of matrix land. Okay, so I want you to go ahead and solve for beta hat. I'm going to give you 2 minutes to do that and go ahead and put it in your application exercise. Okay, so let's go through that. So if you set this equal to 0, I'm going to pull this piece over here, and I end up with 2x transpose x beta equals 2x transpose y. So I can cross out those 2, and I get x transpose x beta equals x transpose y. And this is what's known as the normal equations. This is something that's used frequently in linear models. Okay, so now that we have this, we can use that matrix fact that you can multiply something by its inverse and you end up with the identity. And so we're going to multiply both sides of the equation by x transpose x inverse. And so when you multiply both sides of an equation with the same thing, it just they can cancel out. But what's nice about doing this here is we can get rid of this x transpose x on this side of the equation so that we're left with just beta. And so here we've got this x transpose x inverse times x transpose x, and per our matrix fact, this is just equal to the identity matrix. And so we end up with the identity matrix times beta equals x transpose x inverse x transpose y. And of course, the identity matrix times anything is just equal to the thing itself. And so now we know that beta is equal to x transpose x inverse x transpose y. So that is our estimate for beta hat. There you have it. Okay, so coming back to simple linear regression, when we're dealing with these we have two beta values, beta 0 and beta 1, and this is equal to x transpose x inverse x transpose y, where again, x here is that design matrix, so the first column is all ones and the second column is our predictor value, and y is our vector of outcomes. And so y hat now is going to be equal to x beta hat, And so we can plug in that beta hat that we just derived for y hat, and we end up with x times x transpose x inverse x transpose y. And so this here is just the beta hat that we've plugged in that we just derived. And this piece on the front side, x times x transpose x inverse x transpose, that is known as the hat matrix. And why is it called the hat matrix? Because it puts the hat on y. So by multiplying y times this hat matrix, you end up with y hat.